All right, we're going to cover 2.7, which covers how those measures of center and the measures of spread that we talked about last class work together to analyze data that we're working with. So, to start out here, we're going to just go over kind of the two big ones that are going to be really important as we move forward through the rest of the semester here. So the mean is the balancing point of a frequency distribution, and standard deviation was that typical distance from the mean. Okay, so some of them are falling above, some of them are falling below, but typically they'll fall within this certain number. So, for example, if a data set had just with nice numbers, a mean of 100, and a standard deviation came out to be 10, then a typical data point would be falling one below one standard deviation, so 100 minus 10 is 90, and one above 100 plus 10 is 110. So we're going to see a lot of the values fall between 90 and 110. And if we see a lot of them falling significantly, or excuse me, when we see observations or data points falling beyond this range, it's not going to be very likely. So those more than 2 or 3 standard deviations are going to be unusual or even considered outliers. And we'll get to the specifics of those values here as we go through today. So first thing we're going to do is just practice with some of the things that we talked about last time. So just with Excel, remember finding the mean, we're going to do equals average to calculate that. And there's no label to worry about here. Then we're going to go the sample standard deviation. So standard deviation is built in here. We just want to make sure we use the .s version. And we'll go ahead and just interpret what that means based on, what we worked with last time. So typically, or on average, a data point will vary by about 10.68, whatever our context is, from the mean of whatever context, ours is 15, in general. Okay, so here, a lot of times instead of a data point, we would include our context. So if we were talking about like the heights, we'd say on average, any given height would vary by about this from the mean. Okay, it's not necessarily happening every time, but there's a solid proportion of values that will do that. And that's what we're going to work with by answering these questions here. We're going to find what proportion of these data points fall within one standard deviation. So what we're going to do is find our interval by giving us a low and a high. So on the low end, we're going to take our mean and subtract the standard deviation, just using cell select there. And then on the high end, we're going to do the same thing, but we'll be adding it. Okay. Anytime you get behind here, just pause the video. Okay, you can rewind and watch again. Okay, but we're going to move through here and talk about this interval. So we have between 4.3 and 25.68, and we're looking about what values fall between there. So in general, you can find a proportion just like you can relative frequency, the count over the total. And remember, Excel has a built-in function equals count that counts the number of cells. You can do it with a specific range with the COUNTIF function, but this one it's just really easy to look and grab. So here we want the numbers that are between 4.3 and 25.6, so that'd be starting right after 4 and going to 17, and that counts 5. And then we could do the same thing, equals count, to find the total number of cells. Now obviously for these ones, there's such a small set, we could have just counted by hand. I just wanted to go over those Excel functions for when we have a lot more data values. Okay? And then our proportion is just going to be dividing those two things. This is a nice fraction where we know it's 0.5, but we can say 50% of the data points are going to fall within one standard deviation of the mean. Okay? We're going to do the same type of thing for the next one, but this time we want to go 2 standard deviations above and 2 standard deviations below. So the easiest way to do that, we're still going to grab the mean first, but then we'll subtract 2 times the standard deviation. That way we don't have to subtract it twice. Okay, it's not so bad to subtract it twice, but when we get to 3, it gets a little bit messier. Okay, so there's my low end, and then my high end, I'm going to take my mean and add 2 times the standard deviation as well. So we see that low end is negative, which means all of them are going to fall within the interval on the low side. Similarly here, our high end was above the 36, so we don't have to do any math for this one because we can see that 100% of these data points fell within 2. Okay, because observation, remember, falling significantly below that is rare. Okay. And then 3 standard deviations based on that would also be 1 and 100%, because if none of them fall outside 2, that by default means none of them fall outside 3 as well. Okay, so there are 2 things we can do to come up with standard proportions. We just calculated this for our particular data set. We know nothing about the shape of this data set. We haven't graphed it, and really 10 data points is not going to give us much of a shape anyway. Even on a dot plot, we don't have enough values to really create something that would maybe look symmetric or skewed. But we're going to talk about 2 things today, Chebyshev's inequality and the empirical rule. And they're based on 2 different shapes. Okay, so go ahead and click on this first cell here, and it will take you to this link that gives you kind of the visual of both of these tools that we're going to use. So the first one is Chebyshev's inequality, and that works for any type of data set, no matter what it looks like. Okay, so this is going to be a useful one when we have skewed sets, or if we don't know the shape of our data to begin with. So if you look down below here, we've got on the bottom, remember that mu symbol is the mean, and we've got a scale going on here, and then a percentage or proportion here. So what Chebyshev says is we can find the, excuse me, we can find how much falls within a certain interval using this formula, 1 minus 1 over k squared, where k is the number of standard deviations that we want to set our interval as. Okay, so here's how that works. Right now, I have k being 2. So this would be counting 2 standard deviations above and 2 standard deviations below. So just like what we did before, except these ones are nicer numbers, easier to work with. Okay, it's starting at 50 and adding 10 twice, starting at 50, subtracting 10 twice. So my interval is between 30 and 70, and if we plug that in, it gives us 75%. If I go further out, if I move this out and see k doesn't have to be a natural number. Okay, it can be any real number, even irrational. Okay, but as I increase the number of standard deviations out, the proportion of data values that fall within my interval also increases. And hopefully that makes sense, because the further away from the mean we are, the less likely that that value will actually occur. Okay, so Chebyshev's is very helpful when we don't know what kind of data we're working with. The empirical rule is a special type of distribution, and that is not only symmetric, but it's called a normal distribution, which means it is symmetric, but also our mean, median, and mode fall at the middle, which tells us it has to have the peak in the middle and then go down from there. So it has to have this bell shape to be considered normal. Okay, and a lot of standardized things are normal, like taking a test or heights and weights of someone at a certain age. Okay, they fall the same way typically every time, so they would be considered normal distributions. Okay, so starting with what we ended with on the last one, here's the same mean and standard deviation, or excuse me, yeah, same mean and standard deviation, and we're going to go 3. So this number is 99.7. Okay, when we know the shape is symmetrical in a bell-shaped curve, we can be more accurate than the Chebyshevs in terms of how much of the data will fall within that interval. Okay, so it's much more. And then if I change it to 2 standard deviations, okay, that's my 95%, way more than that 75% that it was with the other rule. So normal distributions are going to have a lot more power when we calculate those proportions. Okay, you'll notice with these, this slider here, it goes from 2 to 3. It is undefined in the middle here because with the empirical rule, we're looking at exactly 1, 2, or 3 standard deviations above or below the mean. Okay, so going back to our notes here, we're going to start with applying this first one. Okay, so we looked a little bit at k as 2, meaning 2 standard deviations, but I just wanted to show you where that 75 came from. Using this inequality, 1 minus 1 over 2 squared, okay, that gives us 1 over 4 here. 1 minus 1/4 is 3/4, changing that to your proportion. Okay, similarly here, plugging in 3 gives us that 0.8 repeating, so at least 88.8, that repeating bar wasn't on there, but at least 88.9% of the data is going to fall within 3 standard deviations. Okay, so what that means is mathematically impossible, okay, based on how the standard deviation is calculated, for more than a quarter of the data to fall more than 2 standard deviations away from the mean. No matter what the set looks like, it's not going to happen. If we go back up to our set, when we were looking at 2, all of our values fell within 2. Okay, but any data set, no matter how you make it up, okay, at least 3/4 of it is going to fall within 2. Okay, so we're going to just practice with this first example. It says, suppose the sales department of a corporation is going to acquire a minimum of $200,000 in revenue each week. So that's their quota that they have to meet. And then they looked at a long-term report over the last 25 years, and on average, the department made $240,000 each week with a population standard deviation of 20,000. What can be said about how often the department did not meet the quota? Okay, so the first thing we're going to do is write out the 2 things that are going to be important for us today, and that's the mean and the standard deviation. Okay, and we're going to identify these values that they gave us. They didn't give us a data set. Instead, they just told us what they were. So it said that on average, this was the number. So we're going to put our 240,000 there. And then the standard deviation was calculated to be 20,000. Now in real life, that standard deviation is probably going to be an irrational number. Okay, this was nice numbers for us to look at some practice here. So we want to know what can be said about how often the department did not meet the quota. So we want to look at the proportion where they did not meet it. In order to do that, we want to see about where this other value, the quota of 200,000, falls compared to the mean in terms of standard deviations. Okay, so we can think of it like this. My middle value is this 240,000, right? Okay, I think I added one too many. So if I go 1 standard deviation above, that equals this plus 20,000, right? Okay, and then I could do it again. And that did the wrong, supposed to do the right formula, but there we go. Just wasn't big enough. Okay, and then same thing. So there's 1 standard deviation above, 2 standard deviations above, and then I can pull it 1 more for 3 standard deviations above. And that's why I did this cell select, even though this is really easy to count up and down. We can also do it this way, equals this value, and we can subtract the standard deviation over here. Okay, and then that's 1 standard deviation below. There's 2, and there's 3 standard deviations below. Well, might have to just type it in. and then this one, since I didn't do the absolute cell select there. Okay, so we want to know what could be said about this quota of 20,000. So here, this is -1 standard deviation, this is -2. So we want to know what was said about this part. Over here, that means our K, which stands for the number of standard deviations, would be 2. And that allows us to calculate, using Chebyshev's inequality, what our proportion would be. Okay, so remember, the formula for this is 1 minus 1 over K squared. And that will be on your formula sheet. You don't have to remember that. So we're going to calculate it just using Excel. Equals 1 minus 1 over. Then we're going to take our number 2 and square it. Now, in the case of this, it was 2 standard deviations below, but to use Chebyshev's, it's the idea of within rather than above or below. So that is within 2. It's hitting that 2. That's important because K has to be greater than 1. So that means we're not putting negatives in here. If you accidentally do, it's not going to affect your answer because when we square a negative, we still get positive. So there is my proportion. So at least 75% of the time, we are within 200,000 to 280,000. So we want to know what can be said about how often the department did not meet the quota. The reverse of that would be less than 25% of the time. So they fail to meet the quota less than 25% of the time. Okay, so looking at how this would change with normal, because we weren't told anything about that data set. They calculated over 25 years, so they probably have enough data to determine what it looks like, but we don't know anything about it. Let's talk about normal a little bit, the special ones. Okay, so we talked about how it has to look like this bell curve. It's going to be unimodal, meaning there's one mode, and that peak is going to be in the middle. We talked about the mean, median, mode are all going to be at that peak, at that middle point. When we're talking about these shapes today, we're going to focus on what's called a density curve, meaning you'll notice these aren't like histograms with different boxes. These are a curve of data, assuming we have lots of data points. And not only do we have lots of data points, but we also have, assuming that our bars, we went and made our histograms smaller and smaller class widths to smooth out this curve. So it's the idea of what happens when we have a lot of data and that lots of data is chunked into very, very, very small intervals. Okay, so that's our curve modeling. Okay. This last part, the standard normal distribution, is taking my curve and instead of starting with the mean and counting by the standard deviation in the actual values of the set, we're just labeling it as the standard deviations. So 0 is representing 0 standard deviations away from the mean because I'm on the mean. 1 is 1 standard deviation above the mean. 2 standard deviations above the mean, and so on. You'll notice there are negative values going to the left. That indicates I'm subtracting from the mean 1 standard deviation. Okay, so when we talk about this standard normal distribution, the mean is going to be 0 every time, and the standard deviation, the scale we count by, just like we counted by up above, is going to be 1, referring to 1 standard deviation. Okay? So we're going to answer some questions here. It says, looking at these, which curve has the highest standard deviation? Okay, so from what we did last time, standard deviation is a measure of spread, or how things are dispersed. If I want the highest standard deviation, that means I want the most spread out. So hopefully we can see that is curve A. Highest mean has nothing to do with the height. Remember, the height of the curve is the frequency. So we're going to talk about the highest mean being on the x-axis, assuming they're on the same scale, and these ones are, which one's literally the highest most to the right. So that is curve C. And then the curve with the most variability. Okay, so that word variability is something you're going to see. So I wrote in this question just so we could see some other ways questions can be asked. That's saying you should be looking at a measure of spread. Okay, so range, IQR, standard deviation, variance. And in this case, we could say, again, the biggest spread is A. Now, I do want you to be careful, because in order to say that this is really more spread out than this one, we have to know a little bit about what context it is, because this one, looking here, is a lower mean and a larger standard deviation, whereas this one is a higher mean and a smaller one. So just like with when we were talking about percentages, knowing a base number, knowing what we're comparing to, the mean, is going to be important for us. Okay, so the proportion is based on 1 standard deviation away, 2 standard deviation, 3 standard deviation, but we have a higher mean and a smaller standard deviation. That means this is really close, tight to where that center value is. And comparing that to A, this is a lower mean, lower numbers, but with a larger standard deviation really indicates more spread. Okay, so this one, still A, but do be careful, because these all are going to vary by the same proportion using empirical rule. But in the case of this one, on the same x-axis, we can compare those means. This one's pretty clear that A is more spread out. Okay, so back to that empirical rule. Okay, I didn't focus much on the percentages other than the first two, because K could not be 1 for Chebyshev. But here's the rules. 68% of all observations fall within 1 standard deviation of the mean, so 1 above or 1 below. 95% will fall within 2 standard deviations, 2 above or 2 below. And 3 will fall with 99.7% will fall within 3. Okay, so almost all of them. So we're going to use these proportions to answer some questions. Okay, we're going back to the example of, excuse me, we're going to go back to the example dealing with my 200,000, that company was our quota, and we had the mean being 240,000 and the standard deviation of 20. Okay, so in general, to answer these questions, we would have to figure out what goes in the middle and what we're counting by to fill out the bell curve, because we were given the distribution as normal. So I've given you a template on this second tab down here, the second sheet, where you can change the mean value, and we said our mean was 240,000. And then our standard deviation was 20,000. And that lets us see the scale here going throughout. Okay, so we've got our 240,000 in the middle, and it's counting up each time. Okay, but what we're going to talk about is how each of these values break down. So I will give you this template, but I will not give you the percentages. That's something that you're going to have to figure out. Okay, so the 3 numbers that we care about are 68, 95, and 99.7. Okay, but in order to answer questions, it's going to be helpful for us to figure out each of these individual chunks. So if I know that 68% is within 1 standard deviation, we can do some quick math to say there's going to be 34% on each side. Okay, similarly, I know that within 2 standard deviations is 95. Okay, but 68 of it is already taken care of. So what I can do is take my 95 minus my 68. Okay, that's going to get me the leftover, but because of symmetry, I can split that in half to get the number on each side. So that's 13.5. Okay, then we're going from 95% within 2 to 99.7%. So we can do that same kind of math here. Take our 99.7, subtract off our 95% that's already taken care of, and you can do this math in your head probably, but then split it into 2 pieces with symmetry. And then the last chunk is outside of 3 standard deviations, so way on these little baby tails here. Okay, with those, we just have the 0.3% that's left over, 100% minus that 99. So 0.3% divided in half is 0.15. And those are the proportions that are going to happen every single time if we know that we're dealing with a normal data set. Okay, so these are the numbers that you're responsible for filling in to be able to answer questions. Okay, so our question, going back to the company, was how often did they not meet their quota? So here's the quota of the 200,000. We want to know how often did they not meet it, and that would be just this direction. So we just need to add up those 2 values, which gives us 2.5%. So the company failed to meet the quota about 2.5% of the time. So I want to emphasize a distinction between Chebyshev's and the empirical rule. Normal distributions tell us what is actually happening, what proportion shows up. It's approximate, but it's pretty accurate, whereas Chebyshev's gives us a minimum proportion. So there was a minimum of 75% where they did meet the quota. That doesn't mean exactly 75% did, because we didn't know what the shape is. So we had answered up above that all we knew is that it was going to be less than 25% of the time. And now that we know it's normal, then we can get even more specific and say it only happened 2.5% of the time, which is pretty low. Okay? We're going to answer some more questions about normal curves. So this first one, shoe sizes of American women are normally distributed. They give you a mean of 8.06 and standard deviation of 1.52. So we're going to just change these values here. Go look at those numbers again. 0, 6, and 5, 2. And that's going to update our bell curve with these numbers. And they're going to ask us a question. So they use the number 11.1. So we're going to do it here. And we want to know, using the empirical rule, what percentage of American women have shoe sizes that are less than 11.1? So we want to go from here over. And using Excel, we can do equals sum to add the values that are from here over. So 97.5%. Okay, and hopefully that makes sense, because 11.1 is a pretty large shoe size for women, and it's saying that 97.5% of the population will have less than that. Okay. This next one is very similar. I'm going to have you pause the video and answer those questions for me, if you would. All right, check your answers for these ones. I do want to talk about this last one. We can't determine the percentage because while we know it's right in the middle, 108 here, those areas don't match up under the curve, so there's a higher proportion closer to that 100 than there is from the 108 to 116. So we could say that it's more than 17%, but we don't know more precisely than that because those areas aren't symmetric like all these other ones were when we look left to right. So be careful with that. We will get into how we can use the normal curve and calculate those actual proportions for the non-right on those standard deviation values. We're just not there yet. Okay. So overall, when you're working on your homework, okay, if you know that the day is normal, you're going to use the empirical rule. If you don't know, or you're told it's not, then you're going to use that Chebyshev's, okay? We're going to skip over this example here and just go to the last type of thing that your homework's going to refer to is z-scores. So the standardization of the data is just talking about taking everything into the same label. So you can compare apples to oranges if you change everything to the number of standard deviations above or below the mean. So that K value that we were dealing with up above, where we counted 1 standard deviation, 2 standard deviations, 3 standard deviations, it has a name, and it's called a z-score. So the z-score is just taking the value minus the mean and dividing by the standard deviation. Now you'll notice I'm able to read this in words because I know what these symbols are. You need to learn those symbols to be able to use your formula sheet that we're working with. Okay, if you don't know what any of this means, then you're going to have a lot of trouble when it comes test time answering some of the questions. Okay, so what we're going to do is talk about how we can use these scores, kind of like what we use percentiles for, to give relative position to compare unlike things. So here's our example of that. A daughter wanted to know how her SAT score compared to her parents, but her parents didn't take the SAT, and if they did, they took it at a different time than she did, so we can't say that her test was the same as her parents' test. The mom and dad took the ACT, and they took it several years apart from each other. So we've really got 3 different tests going on. So you, in order to calculate a z-score, need to know the mean and the standard deviation, and then the score that you're trying to figure out where it lands. So we can see that the girl scored above average, the mom scored above average, and the dad scored above average. So they're all doing better than other people who took the test. But we want to be able to compare them to each other. We can't just take the difference between these because they had different averages. They had different z-scores, at least for, or excuse me, different standard deviations. So the z-score is going to help us know how they did compared to people who took the test, just like percentiles can. And then we can see who has that highest z-score, highest percentile, to compare them to each other. So we're going to do all of this formula in Excel. We do have to use parentheses because we want to make sure we subtract before we divide. We're taking the score that we're focused on minus the mean. Doing it in that order is important because the sign will tell us whether we're above or below the mean. And then we're going to divide by the standard deviation. So this says the girl scored about 1.7179 standard deviations above the mean. Okay? Now, we could pull this down, but I just want to practice here. So equals, parentheses, we're taking the score minus the mean. Okay, that gives us the deviation from the mean. And then we're dividing by the standard deviation to tell how many standard deviations above. So the mom did 1.7021 standard deviations above the mean. So just barely the girl did better than her mom. Okay, and then going to dad next, score minus mean over the standard deviation. And it looks like the dad was lower as well. Okay, you can expect to have to interpret standard deviations. So the answer to this question is the girl scored better relative to those who took her test because her z-score was the highest. Okay, it is important to note that the highest z-score doesn't always indicate the best. We want to look at the absolute value of the z-score Sometimes, because it depends on context, whether it's good to be above average or not. So in class, we discuss things like golf. We want to be below the average because we want to be below par and the lowest stroke score compared to the competitors. We talked about running a race. You want a lower time. We talked about like incident rates of cancer or disease. You would want that to be lower as well. So you have to keep in mind of what each of these different scores represent to know what kind of z-score would be considered good, positive, or negative. Last thing we're going to talk about is unusual observations and outliers. We have done outliers with a box plot. Okay, we did that last time. And that means taking, excuse me, taking our Q3 and adding 1.5 times the IQR will give us some boundary. Anything outside of that is outliers. Same thing, Q1 minus 1.5 times the RQR. Anything lower than that is a boundary. Now this point itself that they're pointing to is not necessarily the lower bound. Remember, we have some sort of imaginary line that's cutting off where that lowest point that's in the data separates from outliers, okay? But that's what we did. One method is using the IQR rule. Another thing we can use is the z-score rule. So normal is within 2 standard deviations of the mean, and then outside of 2 is considered unusual, and outside of 3 is definitely an outlier. Now, I will tell you different books consider outliers different. So you may see questions that say, determine outliers by the 2 standard deviation rule, or consider outliers by the 3 standard deviation rule. So instructions will matter on how to calculate that. We're going to classify based on this. Unusual is above 2, and highly unusual, or outliers, are going to be above 3. So here, given this data set, we're going to identify unusual and outliers if they exist. And in order to do that, we need to know the mean and the standard deviation. Okay. So here equals average. So our mean number is 7.2. And then we're going to do the standard deviation. In general, folks, we're going to use the sample standard deviation unless we are told otherwise, because it says 30 scores from a student assignment where 10 points are given below. Okay, based on that, it's 30 scores from an assignment. I don't know if that's all of the numbers or not, so we're going to err on the side of caution here and use the sample one, which just gives our standard deviation a little bit more wiggle room. It's a larger value compared to the population one. So we have this. We need to figure out what our upper and lower bounds are for 2 standard deviations and what they would look like for 3 standard deviations. Okay, so just like we did up above when we were calculating those proportion of values between, we're going to set up the low and the high. So the first one, we want to take the mean and subtract 2 standard deviations, so 2 times that. And then the high, we're going to take the mean and add 2 standard deviations, so 2 times. So all numbers between 3.6 and 8.6 are going to be considered normal, and then outside of that would be unusual. So high end, we're good, but it looks like just the number 3 would be considered unusual. So the score of 3 points is unusual by the 2 standard deviation rule. Okay, if it was talking about outliers being unusual at 2 standard deviations, you would say it would be an outlier by the 2 standard deviation rule. Okay, and then low, high, we're going to do the same thing here, but use 3 times the standard deviation. And then add it for the high end. Okay, looks like all of our numbers are between that 1.8 and 12.6. So using the 3 standard deviation rule, there are no outliers because all values fall within the interval 1.87 and 12.66, approximately. Okay. Points. And that's it. Okay, if you have any questions like normal, just shoot me an email or come in to see me.